anyway, I don't see any more questions coming across, so I will go ahead and begin the lecture, the actual content of the lecture, where we left off last time. Now, what we were talking about was this thing, I should say where we ended was this concept of the shear center. We said we were able to calculate the shear loads, the shear flows very specifically, and the shear stresses for any beam cross-section based on the assumption that the thickness of this wall was relatively thin. There was no variation across the thickness in terms of the magnitude of the shear stress. The shear stress was thus oriented in the direction, sort of in a tangent normal coordinate system that follows the normal to the thin-walled cross-section. And of course, after we recognized that the total shear on the entire cross-section had to integrate up from the shear flows, we were able to calculate the shear flows and their relationship to the shear load resultant. And this is kind of what it ended up looking like for, this was a top hat style cross-section. And then the next thing we did was go in, and I showed you this slide, and I said, there's this concept called the shear center. And then I skipped ahead a few slides because we ran out of time. I want to also skip back to abacus just for a minute. I'm going to close what we're doing here. So close the results database. And I'm instead going to run a script. So between last time and this time, I was trying to come up with a really good way of demonstrating this concept of the shear center to you. So I, in a traditionally taught class where we were in the lecture hall, I would bring a demo that I had constructed by our machinist that shows a U-channel being loaded, and you guys would be able to play with it. You'd actually be able to apply a load and then see how it deforms. And so instead of being able to do that, I felt it was valuable for you to at least see conceptually what was going on. So let me pause this for just a moment. Where's my pause button? Actually, I can just do this. You know what, I'm going to close this out so that I can get back to the normal database that mechanism that I use. Okay, so this is what the cross-section looks like as a general overview. What I defined were shell elements, much like we just defined in our abacus demonstration, and the type of elements that you guys are going to be using in your projects. And of course, as I hinted at last time, you want to go through and choose these, or I like to go through and choose these ODB display options to make the shells actually look sort of more physically relevant. So the shells that I defined for this particular model were 1 millimeter thick for a, let's see here, 100 millimeter long structure. It is fixed at one end. You can see the X over here is where I defined a constrained boundary condition, which I then tied to all the nodes at this end of the beam. And then at the other end of the beam, I applied a a force, just a force in the x direction. Now, let me go ahead and run this script one more time. That gets us into our display mode. And this is really what I want to show you. So turn off animation for a minute. So again, what I've done now is I fixed the back edge. We're looking now at the front edge, and this X that you can see that my mouse is circling is where I've applied the load. I've applied the load to be in the positive X direction, which in the orientation that we're viewing actually goes off to the left. So I've got an applied load to the left in this view. And you can see what happens when I apply this load. It moves to the left, that's bending, but it also twisted. That's kind of perhaps unexpected that it would twist. Now, the place that I applied the load is approximately at the centroid of the area of this U channel. And so if, sort of intuitively, you might think, well, if I apply the load at the centroid, or I apply it through the centroid, that this thing is going to bend without twisting. Well, it turns out that that assumption would be incorrect. So where else could we try and apply the load? Anybody have a suggestion? So let me ask it this way. If my goal was to get it to twist less, should I apply the load higher or should I apply the load lower? So Scott and Aiden both say lower. Obviously, I agree with you. Let me go ahead and run a second post-processing script. By the way, you guys should play around with these post-processing scripts a little bit. This is slightly tangential, but every time you run Abacus in the directory that you're working in, it creates what's called a replay file. And if you look at this replay file, it's Python. And then you can repeat what you've done in your post-processing using a Python script. And that can automate comparison of different models. You know, if you want to compare model A to model B, you can run this Python script to then create a very uniform comparison. And so I've actually done that in this case for 4 different models at different where I've loaded the cross-section at different areas. So the one that we had looked at so far, I called shear center 0. So this is essentially close to the centroid. Another area I might choose is this one. Now you can see the X in this model. I was thinking to myself, well, you know, I know it needs to go lower. How much lower does it need to go? Well, let's put it down here on this bottom horizontal section right in the middle. Okay, is that going to be far enough down to get this thing to stop twisting while it's bending? And, you know, kind of long story short, what's happening now? It's still twisting. And it's still twisting counterclockwise. So what we've learned is we haven't gone down far enough. Okay, so David asked, did the force change direction to cause the twist? No, so the force that's being applied is directly in the X direction. All right, so that's the second option. Let's, you know, somebody suggested the shear center. Let me go ahead and go beyond the shear center just for the sake of discussion. So here I'm going to show you model 3, which is way low by comparison. Sorry, it's creating a movie right now. It's part of the post-processing script. So now I've applied this load way down at the bottom. You can see I've gone beyond what we know to be the shear center. And now you can see as this thing bends, it's still bending to the left, but now it's twisting clockwise. So you go far enough down and you're going to add a moment that causes it to rotate clockwise. So somewhere between here and here, if we apply a load, this thing is going to bend without twisting, and that concept is the concept of the shear center, the location where if we apply our load through that in a resultant sense, it bends without twisting. And this is pretty close to the shear center. This particular load that I've applied gets us pretty close. Let me pause the time history. And you can see this thing is basically just bending now with no twisting. So visually, the load applied at this location where the X is, bend, no twist, that's the shear center. Okay, so conceptually, I hope you can understand that concept. Now the question becomes, of course, how do we compute the shear center? It's not an easy thing to conceive of until you have a reasonable approach to do so. So here we have that geometric entity. I have a U channel. Okay, in this case, I'm saying, I'm defining this in a relatively general way, so its width and its height don't have to be the same. In the finite element method that you just saw, it happened to be that the width and the height were the same. But that doesn't matter too much. Now, what we do is we apply this concept of calculating the shear flows and then use the resulting shear flows to calculate the shear center. Now, if you remember last time, in fact, I'll go down to the punchline here. This was the punchline. The shear center is the point at which the shear loads must be applied in order to have, there should be a have here, to have no twisting, to no have, boy, that's great grammar, to not have twisting of the beam occur. Now, again, this punchline says the location depends on the geometry, not the load. And hint, it always is located on a line of symmetry. So to do these calculations, I need to now think about, well, it doesn't matter what load I apply, so I get to choose the load how I want to. I'm going to choose to have my load go off in the X direction. There are good choices and there are bad choices. Okay, so I'm making a good choice as an example here. I'll go, we'll return to that choice later in the lecture and see what the implications of that choice are. But for now, I'm going to say that I'm applying a resultant load, Sx, resultant shear on the cross section, some distance based on the experience of what we just saw with the finite element demonstration below the channel. I'm going to call that distance EY, or eccentricity, relative to the bottom portion of the flange. So that's a distance. So Sx times EY now gives us a moment about a particular point. Now, anytime we have a shear resultant load and a thin-walled cross-section, we can calculate the shear flows. This is the equation for calculating the shear flows. It was basically an integral equation. I have greatly simplified it. How did I get away with simplifying it? Well, number one, it's symmetric about this axis. So all the terms related to IXY went away. Also, my assumption was that we have a resultant load Sx. So all the terms related to Sy went away. And therefore, this form is now a very easy form of the shear flow equation compared to what it was in its complete form. So again, what is this? This Q at S equals 0 is a boundary condition term. And this is an integral term where we're integrating from some starting point to some other point within the cross section, the thickness times the position over ds. Now we have different sections of the cross section like we did last lecture, at least the last lecture where we covered this. I'm going to define local coordinate systems. I'm going to define one here at S1 that I'm pointing in the downward direction because I want it to go positively into the geometry from the edge. Here I have another coordinate system S2, another coordinate system S3. So I've broken my cross-section up into 3 different sections. The reason to do that is because this integral then becomes very easy to do in the context of any constant values that may be present in these sections. So here I now can summarize what those values are for each of the sections. I'm going to draw it here for you again just so we don't have to go back and forth. S1 was on this left edge. It started here and went positive this direction. So with respect to the things inside the integral, the thickness is a constant in that section, at least as it's defined. The position, x position, relative to S1 is always going to be at minus b over 2 from the global centroidally based coordinate system. So we can say the centroid, by inspection, the centroid's about in here. So the x distance from that centroid will be minus b over 2, and it'll be constant within the integral. And of course, the last thing is the boundary condition. So the flow at the free edge, which we know to be a traction-free surface, is going to be equal to 0 because there's no shear stress there. So there's a question here from Scott. Scott asks, how could the force be applied at a point that isn't even on the model? So that's a great question. So let me go back to a blackboard here. So if I have this as my cross section, okay, and it goes off down here. So you're asking, well, how can you apply a load down here? Well, the answer to that question is this is the resultant load of any loads that are applied. Now, for this particular beam, if the cross section is uniform, meaning it's that U channel is going to be straight, not tapered, same geometry as it goes off into the distance, that doesn't mean that the end of it can't have something attached to it. So like, you know, if you actually saw this demonstration in real life, we would have what kind of looks like a tuning fork, where we could then apply the load off the cross section, but the beam itself doesn't have the tuning fork as it goes down. So, you know, this is very much, honestly, it's like an airfoil. Okay, in an airfoil like this, you might actually only have one real rigid spar. And then the center of lift could be, you know, say here, and it's passed through ribs and skins to have a resultant on the cross section, but the actual beam that's carrying it is not the same. You know, the rib transfers the load into the beam. You're not loading the beam directly. So Scott, does that answer your question? Does it make sense? A little, yes. Yeah, so today's Thursday. I will actually be in a lab tomorrow that is at Western in the College of Engineering. And if anybody is interested in seeing this demonstration in real life rather than in simulated life, send me a note. We'll set a time, and I'll show you the demonstration in the real world, and you'll see a little bit better, Scott, how this is done and how you can, you know, the load is relative to the beam itself, and there can be a lot of things attached to the beam. All right, so anyway, so these are the constant values and the boundary condition for the shear flow in this section. Then we've defined a new coordinate system, so we're calculating the shear flow in the bottom. In this case, I'm going to say the whole thing has the same constant thickness T. We need to, of course, define the X position as a function of the S position. So since S was positive here, we know when S is equal to 0, the magnitude is still minus B over 2, but then it decreases as you go this way, up to the point where it's equal to positive B over 2 when you get to this corner. So if S2 is equal to the entire length B, so B minus B over 2, you get to B over 2 over here. So it's minus B over 2 here, plus B over 2 here, and linear interpolated between those two. And the boundary condition for this portion is that to say that the shear flow starts at the value of the shear flow from this section evaluated at the corner, where S1 is equal to H. And last but not least, of course, we can do this third section. Same thing, thickness is constant T. Now the X position is going to be positive B over 2 for the entire value of S3. And the boundary condition is at the beginning of S3, the value of the shear flow is equal to the value computed where S2 is equal to B from the bottom section. All right, so Jeremy asks a question. Ideally, shear loads are placed at the shear center. Bending loads are placed at the centroid. Well, not exactly, Jeremy. That's a good question. So one thing you have to keep in mind is that shear loads are the resultant shears on the cross section. So they contribute to bending. Now, when we think, what is a bending load? A bending load, we think of that mostly as a bending moment. But of course, the bending moment is linearly dependent on the shear resultant. You know, dmdz, the derivative of the moment, is equal to the shear. So the shear is dependent on, or I should say the moment is dependent on the shear. So the bending load is dependent on the shear, irrespective of where it's placed. Now, in an ideal world, that's what you're asking. Ideally, are the shear loads placed at the shear center? Well, that's not an easy question to answer. It depends on what your goals are. Let me give you an example. Oh, terrible drawing. Let me draw it bigger. All right, here's an airfoil section. Let's say that we had a U channel in here as our principal bending load carrying spar. Okay, most often there are actually multiple spars. There might be one at the trailing edge, there might be one at the leading edge, but let's just say that you guys are building a DBF plane and you only have enough material for one spar. Now what we're going to find is that, and by the way, in the demonstration we showed that relative to the U channel, the shear center is going to be kind of out here. Now, where is the aerodynamic load? The aerodynamic resultant load is probably going to be closer to, let's pretend it's right here. That's about the quarter chord for this symmetric section. So if it's a symmetric airfoil, it has no moment and the load is going through the quarter chord. So the shear resultant will be at the quarter chord. Now, what does this mean? This means as the wing is deforming due to the load that's applied, obviously relative to the shear center, it's this distance. And so this is going to cause a twisting moment like this. It's going to rotate counterclockwise in this diagram. Now that actually might be good, right? We actively want the wing, as you increase the load, let's say you get a gust, if you design it this way, then the twisting that occurs actually decreases the angle of attack and somehow mitigates the gust. Okay, alternatively, if our only spar were way back here, and here's our shear center, and here's the resultant aerodynamic load, any increase in load would increase the twist and increase the angle of attack, which would, of course, then increase the load even further. So if you had a spar set up like this, you'd get what amounts to a divergent scenario where the load increases the twisting, which increases the load, which increases the twisting, which increases the load. And if it's not strong enough, it could fail. So anyway, where's ideally the location of the load? It depends on your goal. Here for this particular demonstration, we might want to have this built-in safety mechanism where as the load increases, the angle of attack decreases and it mitigates the impact of the gust. Okay, so great question. Nicole also asked a question. Can you explain Q S1 equals H again? Yeah, sure. So here what we have is, so the Q value is going to be a boundary condition. So we're doing 3 separate integrals, so we're evaluating the boundary condition here, here, and here. We have different Q values calculated, each with their own boundary condition. So the value of the boundary condition here has to be the result of the calculation of the shear flow here, evaluated where S1 equals the total height. So S1 goes from 0 to H down here. That's where we're identifying the boundary condition. It's continuity, really, between the two shear flow calculations. Okay, so all of that to say, here are our constant values. I should say they're not all constant. Of course, in one of them, this one here, the position is a linear function of S2. We can then compute the integrals themselves. I imagine you guys can do that relatively easily. The first one had the boundary condition equal to +0. So that doesn't show up here on the slide, but the value of the integration gives us Sx over Iy, b S1t over 2. So it is a function of S1. It's linear because it was a constant previously. When you integrate the constant with respect to ds1, you get a linear S1. The second integration, it was already linear, right? It was linear with respect to S2. So it becomes quadratic with respect to S2. So here's, you get this S2 squared minus, so it's a quadratic minus a linear term. We also, by the way, have a boundary condition baked into this. That boundary condition manifests itself as Q1 at S1 equals H. So we apply H here. So we're getting a BHT over 2. So that actually, that boundary condition lives here. Then, of course, we can calculate the third integral. The third integral was constant with respect to S. So when integrated becomes linear. Oh, by the way, we get a boundary condition where we say that S, Q2 of S2 equals B. So we plug that in, and that comes back to give us this term here. So this one right here is the boundary condition. So this was a boundary condition. This was 0. And so we have a linear, a quadratic, and a linear term for the shear flow. Now, as we alluded to in a past lecture, shear flow, what is shear flow? Well, it's shear stress times thickness. It is a resultant force per unit length. We applied a force, Sx. We now need to calculate the total forces that are present on these segments in order to relate that to the applied force Sx. So as I advised you to do last time, we defined a coordinate system positive downward. So I'm going to draw the resultant force for this segment. I'm going to call that F1. I'm going to draw one this way, F2. Note that the direction is in the same direction as the coordinate system. And here I'm going to draw F3. So F1 and F3 are in opposite directions because the coordinate systems themselves, in a global sense, were opposite of each other, although they were defined this way for continuity reasons. So now I can integrate the shear flows over their length to get forces. Shear flow is force per unit length. We integrate over length to get force. So I'm now integrating these equations with respect to S1, S2, and S3. Since this one is a linear, it's going to become quadratic. Since this one is quadratic already, it's going to become cubic. Because this one's linear, it's going to become quadratic. But oh, by the way, since I'm only interested in the resulting forces, then I can apply the values of the limits into the equation and get the force. We'll do F1 first. This is for subsection 1. That's this one over here. So F1 is equal to the integral from S1 equals 0 to H of Q1. We get a quadratic term, so B S1 squared over 2 times the remaining constants. This is then evaluated at H and 0, and we can calculate the resultant force on this section. So this is what I called F1 is equal to Sx BH squared T over 4. Okay, we can do it, of course, for section 2 also. So this integral is the integral from S2 equals 0 to S2 equals B of the computed Q2, ds2. It was quadratic before it becomes cubic. You can see the result, minus 2s2 cubed plus 3bs2 squared minus 6bhs2. That term evaluated in the limits of b and 0. You plug it in, and here's what you get, F2. And keep in mind, this is now in this direction. F2 is equal to Sx over Iy, 6b squared h plus b cubed t over 12. And lo and behold, we can do this one more time. Here's my integral F3. Again, this is the force now pointing upwards to be consistent with my coordinate system. F3 is the integral of S3, or over the domain S3 equals 0 to S3 equals h of Q3 ds3. That integral becomes, it was linear before it becomes quadratic, b S3 squared minus 2bh S3 times these remaining constants, and then evaluated at h and 0, and lo and behold, what we get is F3 is equal to Sx over Iy, bh squared t over 4. Okay, now, so we've got what amount to 3 forces. These are resultants on subsections of the cross-section. And they have to be the static equivalent of this applied force, Sx. These 3 summed together are statically equal to this one. Okay, now you can see in each of these terms we had the area moment of inertia called Iy. In my own notational scheme, we have 2 subscripts just to be consistent. We can compute that relatively easily. You know, you guys don't really need my help. We can use parallel axis theorem for that. And oh, by the way, this is computed about the centroid. Anyway, we get the parallel axis theorem. We plug that in, and here's what we see. I didn't reside very long on that parallel axis theorem calculation because that's pretty straightforward. You guys can do that on your own, and we're running out of time. But now here's what we get. We get that F1 is equal to Sx, the original load, times some quantity. We get that F2 is equal to Sx, and F3 is equal to Sx times that quantity. Keep in mind, these F1, F2 was oriented here along the centroid, or along the tangent of that segment, right? This is a 2, and then F3 was here. So immediately what we see is F1 and F3 are equal in magnitude. By the convention that we use, this one was down and this one was up, and they cancel each other. So that's a good thing. There is no y component of force present in this structure in its resultant. So these two forces have balanced each other out. And oh, by the way, the calculated F2 also is equal in magnitude to the resultant force in the x direction. So this, what do we need for these things to be statically equivalent? Some of the forces in the x direction have to be equal to Sx. Some of the forces in the y direction have to be equal to 0. And then the sum of the moments ultimately have to be equal to the applied moment. All right, so this gets us back to the slide you've already seen. The resultant forces must be the static equivalent to the shear forces applied through the shear center. You've probably written this down already. The shear center is the point at which shear loads must be applied in order for there to be no twisting to occur in the beam. The location depends on the geometry, not the loads. So, getting to the actual calculation, we can do the moment calculation a couple of different ways. I can say the moments calculated about the shear center, because I've applied the load at the shear center. If I use the shear center as my reference for computing moment, that moment is 0. And oh, by the way, I've assumed the moment or the shear is below the section. Okay, so here I need to then calculate for the resultant forces F1, F2, and F3, what are their contributions to the moment? If I define it as being positive, moment positive counterclockwise, then F1 here contributes F1 times B over 2, positive, relative to this point. F2 actually tends to create a clockwise moment, so that's going to be negative. So minus F2 times its moment arm, which we're assuming is EY. And then F3, again, produces a counterclockwise contribution, so it's positive. So plus F3B over 2. So the sum of all three of those has to be equal to 0. We can solve that for EY. Of course, we know the magnitudes of F1, F2, and F3, so those will cancel. And here we have a computation that gives us the shear center location as measured relative to this point here in the cross section. And in fact, it was this very equation right here, 3h squared over 6h plus b, that allowed me to compute where to put this force in this example where bending without twisting occurred. And so Abacus has essentially confirmed the calculation that we theoretically derived here in this example. Kind of neat, huh? I'm a little biased, of course. I love structural mechanics. I love finite element methods. I this is one of the concepts that I think is really unique and cool about structural mechanics, that you can actually load off the cross section. This idea, this thing that Scott didn't like, the idea that you can load it off the cross section and have it bend without twisting, that's really like totally counterintuitive and very cool. I see one or two of you are smiling. Some of you are scowling. So I hope you're not disappointed by this concept. Yeah, David says, I never knew this existed. Yeah, I didn't learn about this until, about the same point in my career that you guys did. And I'm not even sure I fully internalized it, to be honest, when I was an undergraduate student. It took me until I became a graduate student before it really fully tattooed itself on my brain, and this concept became something that I was so excited about. So anyway, we're out of time for today. It's already 3:54, so we're a few minutes past. I'm going to stop there. When we come back next week, that'll be next Tuesday, we're going to repeat this calculation, or at least the tail end of this calculation, the moment portion of the calculation. And what we're going to do instead is we're going to say, okay, let's pretend I didn't know that it was below. I didn't have the physical example. I didn't have the finite element model to suggest that this was below. If I didn't know, and I made a different assumption, like I assumed it was up here or maybe even up here, how does that affect the computation? So we'll see how that works out next time, and it turns out to work out just fine, as you might suspect. So that'll be the beginning of next lecture. Should take us about 10 more minutes of time. I'm happy to take any questions now about this concept, or really any question. I'll dismiss those who don't need to hang around. Otherwise, I'm going to hang around for a few minutes to let this questions play out. See you guys next week.
I have two questions that are kind of not so relevant, but one, what operating system do you use with distribution of Linux, and then what do you use with the other one that's not Abacus? Is that some other CATIA kind of software, or what do you use for the other one?
Okay, so thanks for the questions, David. So I use, obviously Linux. Most of my, which Linux do I use? I actually have multiple machines. They don't all run the same version of Linux. I happen to have Gentoo Linux on my laptop. So what you're seeing is Gentoo. If you're not familiar with that distribution, it's a distribution that I started using many years ago, and I like it a lot, but it's a love it, hate it kind of relationship that I have with this particular Linux distribution. I started using it because it's a compile your own. Basically, you're rolling your own operating system. And as a result, you have to learn a lot more in order to be able to do that effectively. So I specifically did it so I could learn and become sort of a Linux power user. And it has effectively taught me how to be a Linux power user, and I just have learned so much by using it. But the downside is it tends to not be as easy, and I'll be honest, I've wasted a lot of time over the years trying to make the machine work, when if I'd have chosen an easier Linux distribution, it probably would have just worked fine. But it's my what do you want to call it? Just curiosity, I guess. I like to know how things work, and so I chose it for that reason. But I also use Ubuntu on some of my machines. I use Raspberry. I use a bunch of Raspberry Pis for a variety of things along the way. So there are some good distributions out there. If you're not a Linux user and you want to get started, I'm happy to get you guys started in that. But I would suggest probably Ubuntu is a good place to start, or Fedora, which is a Red Hat based system, or I guess those two would be the ones that I would start with. So that was the first question. The second question was, which software do I use for pre-processing my own models? So that, again, is a question that doesn't have a straightforward and simple answer. Most of the time, if I'm building very complex models, let me shut this down here for a minute. I use HyperMesh. So this, I just built this. I built this beam model in HyperMesh. It took me about, I'm going to say, 5 minutes to get everything how I wanted it. It would have taken me longer than this in Abacus, although I could have done it without any trouble. This is slightly tangential, but Abacus is great at some things, not so good at others. So if you already have a well-defined geometry, or you build, so if you, let's say you create a nicely defined geometry in SolidWorks, and you bring it into Abacus, that the transition from one to the other often has some problems that make it hard to mesh and generate models quickly. And that's because there's this intermediate format, that like a step file or an IGES file, and you're actually losing some of the underlying geometric definition when you use that file format. And so that can make the Abacus user interface somewhat clumsy then for addressing it. Now, if you build your geometry in Abacus, usually you can do just fine. It meshes its own geometry really quite well. But the problem is it's not designed specifically for geometric manipulation. So it's not as good at defining the model. SolidWorks is a lot better. But SolidWorks' finite element package is much more limited. So you get this issue of these specialized software tools are good at one thing, but not good at everything. And SolidWorks, great at defining the CAD, less good at running the models. Abacus, less good at defining the CAD, but much better at running the models. Neither of them is really good at meshing. So this tool that I use, HyperMesh, is a meshing specialized tool, which is much better at manipulating meshes, but it's not as good at geometry. It's better at meshes. So anyway, most of the difficult models that I run tend to be things that don't they don't CAD very well. In fact, let me show you one, just since we're on it. So I'm teaching this other class right now, orthopedic biomechanics, 5200 assignments. Let's see here. So here's another one. Here's a model that one of the students in that class is using right now. So this happens to be a model that it's a femur. And this femur was derived from, let's say, CT scan. And so it doesn't have a really good underlying geometric definition. It's, it's more like stitched together triangulated surfaces. So if you used either of SolidWorks or Abacus for trying to create a good mesh for this and define your models, it would really struggle with this. Most of my models are this type of structure these days, and so that's why I tend to use HyperMesh more than others. And then, usually when that's not the case, I'm still getting CAD from SolidWorks and then meshing it. And I don't particularly like SolidWorks as a finite element package, and I definitely don't like Abacus as a structural geometric manipulation package. So I bring it into HyperMesh, convert it into a finite element model, and then run it in Abacus. So that's my process. Now each user, in many ways, it depends on what skill set you have. I'm better at this one than some of the others. I'm really good at running Abacus from even just the input decks themselves. I'm good at, in many ways, I'm better at actually typing out a set of commands than than trying to define those within the Abacus GUI. Here's an example where I'm just including a mesh. I'm bringing in an outside mesh, and then I'm applying boundary conditions, loads, sections, and so forth. This file is 24 lines long. Isabel was having trouble. The student who's doing this, she spent a couple of hours trying to do this in both SolidWorks and in the Abacus GUI, and had trouble. And it was only 24 lines of code to get it to work without those tools. So, so much of this stuff, it's complicated. It depends on what your goals are. I use about 5 different tools depending on the goals of the project and what type of CAD I'm getting, if any, and what the downstream intent is. Now, for you guys, the reason, so to answer a question that no one has asked yet, but I'll answer it anyway. Why am I making you guys use Abacus, the graphical user interface, to define your models? And the answer to that question is, each one of these tools, SolidWorks, HyperMesh, Abacus, CATIA, they all are a complicated skill set that takes time to develop. And especially if you're going from one to another, now you have software interface issues. And since your models are really pretty easy to define, the Abacus GUI has all the tools to define them. And it's much better for you to work within one tool than to try and learn 3 skill sets and combine them. It's just shorter for you guys. Okay, if there are no other questions, I guess we'll wrap up for the day.